Hey guys, so today we're going to be doing the 2023 AIME number 1. This contest happened like 2 to 3 weeks ago. I thought there were some really interesting problems on this year's contest, so I thought it would be cool to do some of these problems for you guys today. Let's just jump straight into the problems. This is number 1. 5 men and 9 women stand equally spaced around a circle in a random order. The probability that every man stands diametrically opposite a woman is m over n, where m and n are relatively prime positive integers. Find m plus n. So first, notice that we have 14 people because 5 plus 9 is 14. And in any arrangement of 14 people, I'll just draw an example here. We're going to have 7, 8, 9, 10, 12, 13, 14. We're going to have 14 pairs of diametrically opposite people. Actually, I might have forgotten one. Yeah, it was here. This diagram's kind of bad, but you get the point. This one should just be connected to here. Alright, well, I think I forgot one, but basically the idea is that since we have 14 people, I probably forgot to put one in. We're going to have 7 pairs of diametrically opposite people since they're equally spaced around the circle. So out of these 7 pairs, we're going to have to choose 5 of them so that we can satisfy this condition where every man stands diametrically opposite a woman. So without loss of generality, let's just say we choose this one, this one, this one, this one, and this one. So let's just place the men and women there. 1, 2, 3, 4, 5. And I don't really know where my lines went here. Let's just do like 1, 2, 3, 4, 5. So that satisfies our first condition. So we can choose 5 of these 7 pairs in 7 choose 5 ways. And also notice that for each of these pairs, we can either have the man and woman, we can place the man and woman in 2 ways. So for example, just look at this vertical one. The man could be sitting on top and the woman could be sitting on the bottom, or the woman can be sitting on top and the man can be sitting on the bottom. So that's going to give us 2 ways for each of the pairs. And since we have 5 pairs, we have to multiply by 2 to the 5th. And the remaining 4 women are just forced to sit in the remaining 4 seats. Okay, well, I don't know where I messed up, but anyways, for those remaining, to arrange all the men and women, assuming they're not identical, we have to multiply everything by 9 factorial for the women and 5 factorial for the men. And so this is going to be the total number of ways that the total number of arrangements that satisfy the condition. So now we have to find the total number of arrangements, and that's much easier. That's just going to be 14 factorial. So that's just going to be, we can cancel out the 9 factorial on top, and we're left with this on top and this on the bottom. And you can skip ahead if you don't want to see a ton of computation, because now all we have to do is just compute the rest of this problem. So I guess we can just start by doing this. we'll just rewrite the top as 7 times 6 times 5 times 4 times 3 over 5 times 4 times 3 times 2 times 2 to the 5th times 5 times 4 times 3 times 2 over 14 times 13 times 12 times 11 times 10. So these will cancel out, and this will also cancel out with, let's say this. So let's just say 3 and 4 cancel out the 12, and 6 and 5, we can cancel out the 10, and we're left with the 3 on top. And we can say 7, this becomes 4, cancels out with the 14. So now we're just left with 2 to the 4th times 3, which is 16 times 3 is 48, over 13 times 11 is 143, I think. These are relatively prime, so our answer is just going to be 48 plus 143, which should be 191. So number 1 was pretty simple. It's just a counting problem, and it just takes a lot of time to compute the fraction. So let's move on to number 2. We're going to be doing the first 3 problems. I don't know if I mentioned that. I can't remember. So this is number 2. It says positive real numbers b not equal to 1 and n satisfy the equations. The square root of log b of n is equal to log b of the square root of n, and b times the log b of n is equal to log b of b times n. And we want to find the value of n, which is a fraction j over k, j and k are relatively prime, find j plus k. Okay, so let's just look at this first equation and try to manipulate it and see if we can get anything useful. So the left side is log b of n. Our right side is log b of the square root of n. And if you didn't know, the square root of a number is just that number to the 1/2 power. And by our log rules, if we have log b of n to the 1/2 power, we can move this 1/2 to the outside, so it's going to be 1/2 times log b of n. So this is equal to 1/2 times log b of n. And now, if you want, we can use a substitution. For example, we can say x is equal to log b of n. Or you can just immediately see that if this is equal to 4, that's a possible solution. So we can have root x equals 1/2 x is equal to, what is this, like 1/4 x squared. And you can solve the quadratic and get the same thing where x equals 4 is a solution. So we can just say that log b of n is equal to 4. Or in other words, b to the 4th is equal to n. Okay, so that's our first equation. This is what we got, b to the 4th equals n. Now let's look at our second equation. We have b times log b of n is equal to log b of b times n. So again, we can use our log rules. We can say that this is equal to log b of b plus log b of n. This is just 1, and this is log b of n. So we can move this to the other side and factor out log b of n, and we get log b of n times, what is it, b minus 1 equal to 1. And we know that log b, this is equal to 4, right? From this equation here. So we have 4 times b minus 1 is equal to 1. And we just have to solve this equation. B minus 1 is equal to 1/4. B is equal to 5/4. Okay. And we want to solve for n, but we know that b to the fourth is equal to n, so we just raise this to the fourth power. I think the top is 625, which is 5 to the fourth. The bottom is 2 to the eighth is 256. And we just add these two terms, or just these two numbers. It should be 881. So that's our answer for the second problem. And finally, moving on to our last one, which is number 3. Let's just try to order this. I'll move this one away. Okay. Okay, that should be good. This is number 3. A plane contains 40 lines, no 2 of which are parallel. Suppose that there are exactly 3 points where exactly 3 lines intersect, 4 points where exactly 4 lines intersect, 5 points where exactly 5 lines intersect, and no points where more than 6 lines intersect. Actually, did I write this problem down wrong? Let me just check for a second. Okay, I think I forgot one part of the problem. I think it also says, I'll just write it over here. 6 points where exactly 6 lines intersect. Okay, sorry about that. I'll just reread the problem how it's supposed to be read. A plane contains 40 lines, no 2 of which are parallel. Suppose that there are exactly 3 points where exactly 3 lines intersect, 4 points where exactly 4 lines intersect, 5 points where exactly 5 lines intersect, 6 points where exactly 6 lines intersect, and no points where more than 6 lines intersect. Find the number of points where exactly 2 lines intersect. So, first of all, this first sentence is really important. No 2 of them are parallel. So any 2 non-parallel lines will intersect exactly once, because they're just going to like pass each other eventually, since they're not parallel. So the number of for the number of total intersections, assuming all of them intersect, assuming like no more than 3 lines intersect a single point, or actually no more than 2 lines intersect a single point. So for example, assuming if we have an intersection here, assuming that we don't have a third line that goes like that, then we're going to have 40 choose 2 intersections in total. Assuming no 3 lines intersect. But this isn't exactly the case, because the problem tells us that we have all these intersections and we want to get rid of them to find how many points exactly 2 lines intersect. So let's consider the first case. There are exactly 3 points where exactly 3 lines intersect. So what would happen in that case? Let's say we have some lines arrangement like this, and we have 3 lines here. This is only one intersection point, but we have 3 lines, and according to this rule, where we're assuming no 3 lines intersect, we're going to have 3 choose 2 intersections as this one point, which is 3. Meaning we have to subtract 3 for each of these points. And we're given that there's exactly 3 points where this happens, which means we're going to have to do 40 choose 2 minus 3 times 3. Now let's look at our next cases. 4 points where exactly, sorry, I just moved that up. 4 points where exactly 4 lines intersect. So we can do another example. We have this arrangement here. According to our assumption, this point would be counted or overcounted, we would count this as 4 choose 2 intersections, which is 6. But that's not exactly right, because we're actually only getting one intersection from this. So we have to subtract 6 times 4, because we have 4 of these points. And we can just do the exact same thing for the 5 points and the 6 points. For 5, we have 5 choose 2, which is 10 times 5. And then for 6, it would be 6 choose 2, which is 15 times 6. And then we don't have to worry about anything else, because it says no points where more than 6 lines intersect. So 40 choose 2 is 20 times 39 is 780. So we want to do 780 minus 9, minus 24, minus 50, and minus 90. So this is going to be 607. I'll just give the calculations. And that's going to be your answer. And just one important point, when I was actually taking the contest, I almost delayed this problem because I read this last part as find the number of total intersections, which is a different problem because instead of subtracting, for example, 3 times 3, we would subtract 3 times 2, or actually no, we would add 1 for each of these. Because instead of, we want to actually subtract this entire arrangement. So for example, I'll just go through this this first case where we have 3 points where exactly 3 lines intersect. Instead of counting, so we're counting this point 3 times, right? But the problem wants us to count it 0 times, and I almost delayed it because I thought it had to be counted once for each of them to find the total number of intersections. So instead of this answer, I think I put this plus 3 plus 4 plus 5 plus 6 for each of those other cases. So that's just probably one way a lot of people might have studied this problem, if anyone did. So yeah. Anyways, that's gonna be the end of this video. I'll probably post problems 4 through 7. I don't know about problem 6. I think that one's a bit boring. It's just a lot of brute force calculations. But yeah, look forward to the other video, and I will see you guys in the next video.